All right, so homework 3, part D, part 1. I'm going to show how the Maxwell-Stefan equation can be expressed in terms of molar fluxes and molar diffusive fluxes. So, the general Maxwell-Stefan equation is shown right here, where xi and xj are the mole fractions of the component, and these can be shown as either x or y, letting you know if it's either gas or liquid. The orange it is the gradient of chemical potential, which is the driving force of this equation. The green, the Dij, is the diffusive constant for the two components, which this is Googleable. For any two compounds, you can Google this. It's just a constant. Where C is the overall molar concentration, and N is the molar flux of the component. So we're going to first start off by relating this to the component velocities, where I simplified this first term to dj, which is the driving force of this equation. All right, now we're going to multiply the top and the bottom by the concentration. So then that gives us y I c j vj, velocity of j, minus yj ci, concentration of I, bi, over the concentration times the diffusive constant. And now we can simplify this by the flux of I is equal to the concentration of I times the velocity of I, and that's the same for the concentration of J is equal, or the flux of J is equal to the concentration of J times the velocity of J. So this simplifies to yj flux of I minus yi, the flux of J, times the concentration times the diffusive constant of I and J. And this is what the Maxwell-Stefan constant is in terms of molar flux. Now to get molar diffusive flux, we know that the flux of I is equal to the diffusive flux Ji times plus Yi times the concentration times the net or the total flux. So we can input that into this equation. And that then gives us Yj times diffusive flux plus the mole fraction of I times the concentration times the net flux minus Yj fraction of J times diffusive flux of J plus mole fraction of J times concentration and net flux over concentration times diffusive constant. Alright, so now let's open these parentheses up. So then that gives us this is supposed to be Yj, right? Yeah. Over concentration times the diffusive flux of Ij. And then this term and this term cancel out. So the only thing that's left is the fraction of I times the diffusive flux of I minus fraction of J times the diffusive flux of J over the concentration times the diffusive constant of Y and J. And there we go, and that is the Maxwell-Stefan equation in molar diffusive flux. All right, now I am going to show how for ideal mixtures the reference chemical potential is at the pure state and how to derive the mole fraction respective coordinate direction. So we are going to take the general Maxwell equation and in this set the chemical potential is equal the chemical potential at standard state so to change this, so the chemical potential at standard state, to get rid of that, we have to set this equal to RT times the natural log of the mole fraction. And then we have to take the derivative of this. The derivative of the gradient is the mole fraction over position. So we'll substitute this in and take the derivative. And this is equal to RT over 1/2 xi dz. We take the derivative, RT is constant. And we put this over, and then we have to relate it back to the derivative or the gradient. And we plug this back into the equation. So then that gives us xi RT 1/xi gradient of xi, the mole fraction over position, RT equal to that. And then we can go ahead and cancel out some things. So the Stefan-Maxwell equation is equal to the gradient of xi over dc. Now for this part, I'm going to show how Maxwell-Stefan equations can simplify to Fick's law for an ideal binary mixture. So we are going to take the molar diffusive flux equation. No, we're going to take the molar flux equation. No, I was right. We're going to take the molar diffusive equation, molar diffusive flux equation. Oh my goodness. Blah, blah, blah. copy this. All right. And then we're going to set I equal to 1. So then that gives us di, or d1, the driving force of 1, and j1. And it's going to be this is the mole fraction of y, a mole fraction of 1. This is molar diffusive flux 1 minus mole fraction of 1, diffusive flux of 1 over C concentration times diffusion coefficient 1 of 1. And then we're going to add, since it's a binary liquid, it's going to be mole fraction of 1, mole fraction of, or diffusive flux of 1 minus y2, fraction of 2, diffusive flux of 2 times concentration divided by the concentration times diffusive coefficient from 1 to 2. This is actually 1. Alright. And then this whole term cancels out because, I mean, if you're doing it through the same component, there's going to be no change, so it just cancels out. So it turns into driving force of 1 is equal to the summation of n1. Alright, so then that gives us mole fraction of 1 times the diffusive flux of 2 minus mole fraction of 2, the diffusive flux of 1 times the concentration times the diffusive coefficient of 1 through 2. And if we think of a mole fraction, it always equals 1. So y, the fraction of 1 plus the fraction of 2 is equal to 1 for ideal situations. And then if we think of diffusivity for steady state or ideal gas, diffusive flux of 1 plus diffusive flux of 2 is always equal to 0. So diffusive flux of 2 is equal to -1. Negative diffusive flux of 1. So we can implement this into the equation, or let's rearrange this one too. For y2 is equal to 1 minus y1. Alright, so now let's put this into the equation. So I don't know why I keep writing I, it's d1. So driving force of 1 is equal to the summation of j1 and alright, and then so it's y1 times negative diffusive flux of 1 minus, this would be plus 1 minus y1 no 1 minus y, mole fraction of 1 times diffusive flux of 1 times C over concentration times diffusive coefficient of 1 to 2. All right, and now we're gonna expand that. So all right, so then these terms cancel out, so then that gives us and then this looks familiar because if you rearrange it, it gives you Fick's law. And that makes sense because Fick's law doesn't work for more than 2 components that are ideal gases. So part 4 of question D, the relevance of the application of the Maxwell-Stefan equation is being able to relate many different components, as many as you needed to or wanted to experimentally, and get the different molar diffusivities or the molar diffusive fluxes, like how we've modeled in the previous 3 parts of this video. So that's why the Stefan-Maxwell equation is very, very important and a very powerful tool.